No, that's fine. Whatever problems I have, I think. All right. My high-tech new method failed, so I'll go back to my low-tech old method. All right. This one. All right. I think we're good to go. So maybe start with some administration stuff. So you probably have seen that homework 1 is being posted. It is due on Feb 3rd at midnight. Okay. It has questions on recursion. It has questions on divide and conquer. It has a question from today's lecture. So if you see something that's like, what are you talking about? Don't worry. Cover today. And it, just like homework 0, I have the LaTeX, I have the PDF. You know, put your solution boxes in there, as I mentioned, as someone asked. So it should be pretty straightforward. And I mean, in terms of just constructing them, I'm not saying the solution. So the instructions are all there for the homework. Just like I said, I've written this out, you know, hopefully clearly that you have to reason carefully about what you're doing, like we try to do in class. Yeah, that's basically all I have to say. You will need to recall the master theorem that I described to you, and you'll apply these principles in divide and conquer that we'll be talking about, and that's it. Okay. So, I'm sure you'll have more questions as time goes on, but that's basically it. So that's the first thing. The second thing, which is going to take a little bit more work for you all, is the project. So, as I mentioned early on, we're going to have one of the elements of this class is a project. It's so there's assignments, there's a final exam, there's a project, and one of the things we've tried over the years is try to think about what does it mean to do a project in an advanced algorithms class, right? So, a lot of other classes, you build some system, you do a data mining class, you build do some implementation project. And we've tried different formats in algorithms class. I think, but one thing that we thought was helpful, just that students seemed to like and was also meaningful and interesting, was to take take a problem that people have looked at some interesting solutions for, theoretical solutions, and actually try to implement them to see what happens if you try to implement these things in practice. The reason this is interesting, and a couple of you were at the talk earlier that we had to sort of skip out of, there's this tension between how you reason about problems formally, from the point of view of doing worst case analysis that we do in this class, and what happens when you try to deploy these algorithms in practice. Now, we don't do algorithm design, at least we don't conceive of the formal reasoning about algorithms as purely for the purpose of figuring out what's practical. That's not why we do it. We design algorithms for problems to understand the complexity of problems, to understand what computational tricks are needed to attack a problem and try to solve it efficiently. Sometimes, and more often than you might think, these solutions also lead to things that are very efficient in practice. But when you start looking at how problems work in practice, you run up against a whole host of implicit assumptions about data, implicit sort of patterns in data that the algorithm may or may not be exploiting, that make things look different in practice than they do when you prove things in the worst case. And so one of the reasons to try and implement algorithms is to understand this tension between what we guarantee formally is always true and what actually happens and what tricks you might be able to employ to actually make things work faster. Some tricks do not compromise on correctness, they're just heuristics or hacks that kind of optimize the implementation. Some things do compromise correctness, but for data sets that people tend to look at, they're okay. Of course, it gets a bit hard to reason about why they're okay and why things should be expected to work. But that's where there's sort of an interesting sort of set of tools around that, how to reason about algorithms in practice. Now, we won't cover that in the class, right? I'm not going to teach you how to implement theoretical methods in practice. But by doing a project where you have to read a theory paper, understand what the algorithm is telling you, using the knowledge you built from this class, and then implement it, even in a vanilla way, you get a sense of the gaps and also the challenges of trying to sort of, what happens. Certain primitives that look easy in theory are hard to practice, certain primitives that look hard in theory are actually very easy to implement, even though they're hard to prove things about. And understanding that trade-off is interesting. So what I've done is, and I've borrowed this from Alicia's class from last year, there's a list of papers that sort of I talked about are interesting sort of topics that have connections to relevant practical problems and have interesting theoretical results in them. And some of these papers actually have nice implementations of these things as well. So your challenge will be take one of these papers, take one of the algorithms they talk about, and implement them. And if you are feeling sufficiently inspired, maybe think of ways in which you could do things better than what the algorithm is. Right? Maybe tweaks, maybe heuristics, maybe something that you realize is something the algorithm is not doing in its analysis that you could do better. Who knows? There are all kinds of possibilities here. So what I'm asking you to do by February 8th, so that's a Friday of the following week, is come up with a proposal for which paper you're going to pick and what you're going to do. And this proposal will consist of basically one page. You're going to describe your group, which will be basically 2 people or less. You're going to just make mention of the paper and give a link to it. You're going to tell me which algorithm you're going to implement. You're going to talk about what data sets you're going to test it on. You can't implement something and not test it. And so all of the things should be available. The paper should be available. The data sets you use should be available. Usually, if a paper uses certain data sets, they're usually available. If they're not, then it's up to you to figure out another data set that might be appropriate and defend that choice. And that's it. So it's one page. The easiest thing really would be to pick something from that list, and it doesn't matter if multiple groups pick the same paper, that's fine. You're welcome to choose your own, but I have a higher standard for papers that you come up with. In my experience, people are not necessarily very able to find papers that have the right level of theoretical sophistication that makes the implementation interesting. And so there might be a lot more back and forth. But if there's more back and forth, that means more time. So I would say, unless you have a really strong reason not to pick any of the papers on the list, which is hard to imagine, or you really understand this other paper, and then you can argue convincingly that it captures the ethos of sort of a nice, elegant theoretical solution that you want to implement. Unless you can do that and defend it to me, I would say pick one of the papers. So, but I will leave open the possibility, however small. There's more instructions on exactly how to construct this proposal document, which we'll upload like an assignment for February 8th. So again, we'll probably have more questions about this, and so feel free to post questions on the outside of asking the class. Okay, so these are the two sort of administrative items I wanted to bring up before class starts. As class starts, before we get into the actual lectures. Are there any questions?
Is there any restriction on programming language?
No, I don't know. One thing that might be worth considering is if they use a particular language. One advantage of using the same language, if you can, is that you can do a direct comparison. One advantage if they use a language that you think is awfully slow and terrible, how could anyone in their right mind ever use something like that? Then pick your own and see if you can do that. I'm looking for, yeah. More or less. And in Canvas, there's a way to basically assign yourself to groups. So I've created essentially roughly 20 project candidates. I'll create more, but like 20 project groups, imagining that some of you will be in pairs and some of you will be single. And so you can literally sort of drag and drop yourself into a group. So if you have a partner and say, oh, okay, we'll be group 5, just drag and drop, and you can name your group afterwards if you want. But that's basically it. So I would, so please do that as well, along with submitting it. Because once you do that, then the submission, the way Canvas looks, is going to be group submissions. You don't have to submit something. Yeah. So again, I'm sure you'll have more questions about it. But start thinking about this now. Look at the list, start looking at the papers, maybe a paper catches your eye. Oh, that seems interesting, the title. Go look at it, see what comes in. Okay. All right, let's continue. So we're going to finish up divide and conquer today, and I'm going to start moving a little bit more quickly. But I want to point out one sort of design paradigm in divide and conquer that we haven't yet considered. So the divide and conquer paradigm, once again, I'll do this more schematically because we've seen the more formal way of thinking about this. You have a problem input, and you break it up into smaller pieces, right? And then you recursively solve the problem from the small pieces, and then you merge them up together to get a problem solution to the original problem. So essentially the divide and conquer step. So going down, you divide, and going up, you conquer, right? But there's often a third step you can take in the middle for certain problems that's even more effective. And that is where you essentially throw stuff in. So in this case, what you might decide to do is after doing the divide step, you decide to throw away some of the pieces you get. Just not look at them. You divide and just get rid of them. You don't process them, you don't do anything. Now this seems a little weird. Why on earth would you want to do that? And how could you ever expect to get a good answer to your problem if you do that kind of thing? But A, it turns out it's a very good idea from an efficiency point of view, and B, there are actually a number of problems where this is in fact the right thing. And this is an example of a strategy to continue our military metaphor. It's called decimation. Now, I don't know how many of you have heard of the term decimation in a non-computer science context. Non-computer science context. Would one of you like to enlighten the class of the bloody origins of this concept?
I just know that it's destroying something.
Anything more specific?
Carpet bombs.
Carpet bombs.
From planes.
No. There are no planes involved in this story. This is 2,000 years old.
I don't know the etymology, but I know that it's more specific than just destroying something. It's to reduce by 10% or reduce to 10%.
Exactly. So the question is, what are you reducing by 10%? That's where it gets rather gruesome. It's not the number of limbs in your body, but it's equally bad. But yeah. Any one? So the way the Romans decided that they needed to enforce discipline in the ranks when they were having mutinous sort of crews, was by a process called decimation, where they would line all the soldiers up and shoot every 10 as a way, as a lesson to the others, sort of stay in line. So that gruesome analogy is what we're going to be using here as a sort of a design paradigm where the pieces you're going to shoot, unfortunately, are parts of your input, hopefully with less violence. And so the idea of decimation is again this idea that once you divide, you throw away parts of your input and then recombine. And so there are two ways to think about why this is a good idea. One is, like I said, an efficiency point of view. But let me first argue that you've actually already seen decimation in real life. So a simple example of decimation or bias is binary search. So how does binary search work? So the binary search problem, I have a sorted list. So I have a sorted list. Okay, that sorting is important. And I have a query. And I want to know, is X in the list? Right? It's a membership problem, or a dictionary problem. I have a bunch of things and I have a new thing. Is the new thing in the list? And the easiest case of this is when the list is sorted. So presumably you all know how this game is going to be played. We're going to look at the item in the middle and we're going to compare it to the query X. If the item in the middle is bigger, then we know that X has to be on the first half of the list. If the item in the middle is less, we know that X has to be in the second half of the list. So we go that half, and again we ask for the middle item. Right? So we all presume we've seen this before. Right? So you have that, you sort of. Okay. Why is this an example of divide and conquer? Well, what we're saying is this. We're saying, I have a list, and I have a query coming in. Right? And what I'm saying is, I'm going to do essentially the conquer step, if you wish, first, and say, check with the middle item and see which way I have to go. Right? And then once I do that, I either decide to recurse on the left piece or the right piece, but not both. It would make very little sense to actually look at both sides once I have my list sorted and I've already checked to see which side. So it's almost like I took a problem, find an element in a list of size n, and I've reduced it to, well, there are two parts. There's n over 2 on the left and there's n over 2 on the right. But then based on the answer to my query, I've removed one. Yes? You see? So it's not that you're dividing ahead of time, checking both answers and deciding what to pick. You're saying, no. I'm going to ask a question first, and based on that, I'm going to decide to ignore one side or the other. I'm dividing with one. And if you then say, well, okay, that's all well and good, what does a recurrence look like then in that case? Well, then we can say that the time taken to search a list of size n is some constant amount of work to do that first check with the middle element. So we'll say it's this constant amount of work, plus the time it takes to search a list of size n over 2. By the way, homework 1 is going to have a question that explores this problem of what happens if n is odd or even. So you're going to have so hopefully by the time you finish that problem, you will be more willing to let me get away with stuff like this and not say, well, it's what if n is odd. So this is a recurrence of the kinds we've seen before. So if you write this in the form 1 times t n over 2 plus c, this can now pattern match with my a times t of n over b plus g of n. And then we know that the relevant things we have to compare are going to be, we're going to look at basically, let's just see, so g of n is a constant, so we're really comparing a times f of n over b versus f of n. This is c. This is c. They're both the same, right? Because a is 1 in this case. And so the answer is going to be f of n log n, which is equal to log n. And so binary search takes log n. So again, if you look at the recurrence, what the recurrence is telling you is that what I did not have, which would be something you might see in, say, a sorting recurrence, is this extra 2 here. I did not have that. I did not actually break into two parts and work on both. I only worked on one of them. I threw one part in. And that's very important because that's what essentially gives you this much more efficient result, a log n, instead of something that might look much more expensive. In this case, might look linear. So more generally, you can imagine that a recurrence that involves decimation, right, looks something like an algorithm divides an input into parts of size n over b, and doesn't take b of them, which would be what you'd expect if you divide into parts of size n over b. With b of them, it takes a of them, where a is less than b, plus f of n. Right? And if you remember how this recurrence is supposed to work, again, roughly speaking, the divide step dominates if you look at the expression n to the log of a base b versus f of n. These are the two terms you're essentially going to be comparing to see which one is more dominant, the divide or conquer. And since a is less than b, this term here is much, much smaller than n. It's small above n, which is strictly smaller than n. So all that happens is that the term f of n is going to dominate your overall cost. And so that's going to be the runtime of the overall procedure. And if a is 1, then this actually becomes, one, a constant. Because log of 1 base anything is 0, and so n to the 0 is a constant. So in other words, again, going back to the recurrence to the algorithm, if you can find a way to divide a problem into pieces and be able to throw away a constant fraction of those pieces, we are guaranteed that we're going to have a very efficient algorithm. And this is the paradigm of decimation. Binary search is the simplest example you can find of such a paradigm. But of course, if that was the only example I could come up with, that would kind of boring. But there are many, many more. And the one we're going to look at today, in fact, one that was also mentioned in the talk today morning, a while ago, is the problem of finding medians. So it's a very old algorithm. So hopefully you all remember what the median of a list of numbers is. A median, so if I give a list of numbers, x1 through xn, the median is sum y such that the number of xi less than y is equal to n. Half the elements are even. Again, if n is even, y might actually not be an element of the set, or it might be the whole continuum in the middle. If n is odd, then one of the elements of the set will be, in fact, will be n minus 1. And the question we have is, how do you find a median? So there's a trivial algorithm to find a median. It involves sorting. And what would that mean? If you want to find a median and you're allowed to sort, what would you do? Not a question, it's a simple question. Takers. I'm trying to sort of distribute the hands over the entire group. So if you have your hand up and you're wondering or not, because your count has gone up very high in my head, so I'm trying to wait. Anyone? If I can sort, how do I find a median? I need more specifics than that.
So we have to find the median.
So no, let's back up again. So this is part of my training for your homework, right? So I give you a list of n numbers. Give me an algorithm to find a median. Now done. Step 1.
So step 1, should make sure that this is sorted.
How do you make, suppose it's not sorted? Do I give up?
Then you have to find.
Okay, so step 1 is to sort the, right? Okay, step 1, sort the list. Step 2? Step 2, yeah. Take the middle number and just report it, right? Okay, so your 2-line algorithm for finding the median is step 1, sort. Step 2, take the middle element. By definition, it will be correct. Okay, how long does this take? No, it doesn't. You tell me what you want.
Merge sort.
You get to pick. I'm not holding your hands behind your back. You want to pick merge sort? Pick merge sort.
Yeah,
So
then
don't be indecisive. Tell me.
yeah, then I can make everything diagonally.
Okay, so back up. Step 1, use merge sort to sort your list. Step 2, pick the middle element. Step 1 takes n log n time. Step 2 takes constant time. Overall running time n log n. We have an algorithm. It is, clearly it is correct because the median element, by definition, the middle element, we have running time. You get full points for this one. Right there. Good. But now I come along and say, no, n log n. That's for amateurs. I want linear time. And this is where the whole problem mean finding comes in. Because if you want a linear time algorithm for mean finding, you cannot sort it. That's out of the picture. You go to something else. And now you're thinking, how on earth am I supposed to find the median if I can't sort? Clearly, I need a sort. And then you have to say, well, does it really matter if things are sorted or not, as long as I can somehow make sure this element is in the middle? Think about this a different way. Suppose I gave you an element and said, hey, this is the median. Don't trust me. I know what I'm talking about. I've been doing this for 20 years. This is the median. How do you check if I'm correct? How do you know? You don't trust me. You should never trust me. Not when I say so. But how would you be able to check? Can you check if the thing I gave you is the median quickly? You're nodding in the back. How do you do it?
We can linearly keep checking and keep a count of the number of numbers that are less than or equal.
Right? So if I gave you a number and said this is the median, and gave you like 10 pages of guarantees, you could say, that, I'm just going to check myself. And you can do that in linear time. So you can check if an element is a median linear time. So maybe there's some hope that you could actually find a median. I'm not saying checking is the same as computing, right? What P would be equal to NP. But in the absence of solution, P versus NP, suppose we could use that fact that we can verify essentially not just the median, the rank of an element in linear time. Could that help us? And that is the basis for an algorithm that I'm going to describe that helps you find. And is going to use this principle of decimation. And in fact, sometimes the best way to solve a problem is to make it harder, not make it easier. People will say, oh, they'll make it easier. That's always the wrong. Sometimes you have to make it harder. So I'm not just going to solve the problem of finding median. I'm going to solve the problem of finding the kth highest number for any group. So you give me k's, I want the kth highest number, and I'll find it. Of course, the median is a special case where k is n over 2. And of course, if k is equal to 1, I want to find the max, and that's pretty easy to do in linear time. Right? Or find the min. So what I want to do is solve the k selection problem of finding the kth highest number. And the idea I want to exploit is that this number, so if you think of my list, right, and I have my numbers in the list, the number I'm looking for, the thing I'm looking for that will give me the answer is somewhere hidden inside. I don't know where it is, but it's somewhere hidden, and I have to search for it. So what I'd like to do is somehow be able to eliminate at every step a large fraction of things that I'm pretty certain are not the answer. Yeah? If I can do that, then in the beginning I have n items. After that I have n over 2n over 3 items. And maybe I have 2n over 3 times 2n over 3 items, 4n over 9. Then eventually, hopefully I'll get down to 1 item. That is the 1 item. And decimation, or some form of removal, is going to help me. Okay. So if I want to find a weak median, what I'd like to do is get some handle on a way of pruning out things that cannot be medians. And the question is how? That's what we're talking about. And the trick, and this is a very old algorithm, it goes back to the early 70s, so it's one of the earliest algorithms sort of in the field in general, in computer science, but it's also very, very clever. It's very clever in a way that sort of is in some sense not obvious even now. It's not, when I tell you this algorithm, it's not going to seem like, well, yeah, obviously that's what we should be doing. But let me describe it. And it looks somewhat arbitrary, but hopefully as I explain it, we'll see why it kind of makes sense and why it works. So remember, I have n items. Right? And for now, again, I'm going to assume that I can divide n groups any way I want. So what I'm going to tell you is I'm going to divide n into groups of 5. And again, the assignment will actually talk about why 5. Right? So I'm going to arbitrarily divide them into groups of 5. So I'm going to draw them this way. So I'm going to have my first group of 5 here, the first 5 elements in my list. And I'm going to have the next 5 elements in my list. And the next 5 elements in my list. And so on. And I'm doing this arbitrarily, right? Literally take first indices 1 through 5, indices 6 through 10, and so on. So how many groups are there? There are n over 5 groups. Okay. All right. Now what am I going to do? What I'm going to do is identify the median in each group. Now you can see why I chose an order. It's always one of the elements. Now this is hopefully easy to do. I have 5 elements. I literally just try them all and figure out which one to solve if I want to. It's going to take constant. So I'm going to mark off those 5 medians. Maybe the element was this one, maybe it was this one, maybe it was this one, and maybe it was this one. I have these n over 5 medians. Okay? And then what I'm going to do, this is where it gets a bit better. I'm going to I'm going to compute the median of medians. For cricket fans, it's like man of the match. Not a cricket fan, I'm sorry. So I'm going to take the medians, and I'm going to do this how? With my magical median algorithm that I don't have, i.e. recursion. I'm going to recursively compute the median of these medians. There are n over 5 of them, right? One for each group of 5. I'm going to compute it from all using magic recursion. So let's say that magical recursive median is the one that's here. Okay, that's one of the medians. Let's say it's this one. This happened to be the median of medians. Okay. What can I say about where that number lies with respect to the truth? Can I say what I would like to say is that this number is kind of big. It's not too small, which means that if I look at things that are below it, there are a lot of things that cannot be the median I control. That's what I want to use this number to get rid of a bunch of things. Remember how in binary search I asked a simple question and I used it to get rid of half my input? It's going to be a lot more work here. I did a lot more work to find this element. And I still want to get rid of things. But I want to say something about the things I get rid of, that I actually can get rid of nothing. So let's think about this median of medians. What can we say about it? First of all, we know that each purple point has 2 things below it. Right? Because it's a median, there are 2 numbers below it. Yes? Moreover, the median of medians is the median of n over 5 things. Right? So the median of medians, this one, has n over 5 medians below it. Or n over 10. No trick. No, thank you. That was not a trick. I actually didn't say. Something that I do. Right? And each median has 2 elements. Below it. Right? What can we say about the total number of elements below the red median. So here's a claim element. Let me write this down. So why is that? Remember that the red point has n over 10 medians below it. Each of those medians has 2 more points below them. Right? So this red element has each of those n over 10 medians plus 2 more for each of them. So that's 3 times n over 10 elements.
Purple thing you say that has 2 elements below it, you mean in a group of 5?
In a group of 5. Okay. That's right. So each group of 5, I did by definition, I chose the median. So it has 2 things below it. Yeah, okay. Let's just contemplate that. Yeah.
And that, actually, can you go back and explain the n divided by 10 medians below it?
Yeah. So there are n over 5 groups. Each one is sending up a candidate representative to the legislature, but they're all going to be defined a new median. And so there's this n over 5 purple points. Yes?
Yes.
I take the median of the n over 5 purple points. Half of those purple points are below.
Okay. Thank you.
Yes? Okay. So this red point has 3 n over 10 elements below it. By the way, can you make the same reasoning and replace below by above? You can. Just everything reverses. So if you imagine the list as actually being sorted, which it isn't, right? That red point is somewhere in the range from above 3 n over 10 to 7 n over 10. Right? I don't know where it is, but it's somewhere there. Which means that, so think of it this way. Suppose I say I want to keep all the points that are above the red median. Is that going to work? I want to throw away everything that's below the red median and keep everything above it. Will that work? Will that always work? Will it work at all? Is there a situation in which it will work? If I keep everything that's above the red median? What do you think? So my recursive step, my filtering step, my decimation step is going to be, okay, I got this answer, this red median, this magic point, I'm going to keep everything above it. Will it ever be okay to do that? Suppose that, remember, that red point could be anywhere in this range from here to here. Suppose it happened to be this point right there. This would be a valid thing to do. Why? Because the median is right here. So if you picked all the points that were above that red point, you'd be okay. But this could also go badly wrong. When could it go wrong? If it turned out that the median happened to be on the other side. Oh, sorry, the red median of medians happened to be on the other side. We don't actually know right now where it is. We just know that we can guarantee wherever it is, it's in that range somewhere. We don't actually know where it is. So, but we can't actually come up with a rule to say use this to filter things. But if you remember, I just said if I give you an element, I can check where it is in an unsorted list in its rank just by scanning the list. I can scan the list and count exactly how many items are above it. So I can check to see how many items, if it's above the median in rank or if it's below the median in rank. And either way, I can be sure to then eliminate 3n over 10 of my. So maybe this is a little bit too much speculation. So let me try to write this down a bit more precisely. What I'm saying is this. So step 1, break into groups of 5. Step 2, compute median of each group. Step 3, compute the median of the medians. Right? And then I'm saying step 4, find the rank or the position in the sorted order of the median of medians. Right? Yes? And step 5 is, let's call this rank R. If R is greater than n over 2, throw away all points. So the rank of my red median is more than n over 2. Which point should I throw away? Let's move back to this picture. So my rank is more than n over 2. Which point should I throw away? I heard mumbling, so I can hear.
Point on the right.
3 over 10.
Not a number. Well, who said points to the right? Yeah, can you explain?
Because you'll be searching for a median before before greater than half of the end. So there's no point looking at the right half.
We can be sure that it has to go away. It's not there. So all the points are right. And if it was less, we throw away points left. So in particular, if we throw away all points above the MOM, right? Else, if R is less than n over 2, throw away all points below . And if R is equal to n over 2, then you're done. You actually got lucky and found the median in the first step, which is fine. And then, once we're done with that, repeat on what's left till you get down to the point where n is at minus 5. This is the entire median finding point. I have not yet convinced you that any of this is correct. I'm going to give you a fully specified algorithm if you don't care. But this is the idea. To make this fully specified, I have to put in a couple of things. First of all, I have to say, the algorithm really is finding the, like I said, find the kth highest element. Okay, and I'll do all of this as before, but now if I want to find the kth highest element, if the rank of my element is more than k, then I throw away the stuff higher. If it's less than k, I throw away the stuff below. Right? So if it's more than k, so I'm going to replace this by k, I said k, which was n over 2 for the median. Repeat what's left, and then since you're calling this recursively, you have to pass a value for k. In this case, sorry. So maybe I should write this differently. K, calling calling K select. Else, if it's RLM, you find the elements below K, calling what do I want to call? I want to call K minus R select. In other words, if you have your list and the element this pivot, this median of medians is above the element you're looking for, then in the remaining list you still want to find the kth highest element. But if the one you picked is below, then now its rank is changed because you've taken away R elements below it, and so you have to modify the case. Which is why I said you have to generalize this question, not to just compute median, but compute the rank of find the kth highest item for any case. That's why the recursion actually. So now this is more fully specified, but we have still no reason to believe this is either correct or will work efficiently. We need to reason about it. So let's first talk about the correctness, because that's possibly a little bit easier to reason about. And as always, we should make sure it's correct before we try to analyze it. If you think about all of the first 4 steps, how about you just ignore them from the correctness point of view? Just say someone gave me an element. It's this red point. I don't know how they got it, but they gave it. Okay, it's just some element in the set. Are step 5 and step 6 correct? Well, in particular, step 4, sorry. You get this median. So imagine that I didn't do steps 1, 2, 3 at all. I just somehow magically pulled a point out of that. And then I run step 4, step 5, step 6. Will my algorithm be correct? So this is the first thing to think about, right? What parts of this do you need for correctness and what parts of it do you need for efficiency? I am saying that for efficiency, I can ignore those first 3 steps. All I have to do is find something, any element. So what does it say? I took an element, I found its rank. Its rank was 10. I wanted to find the 46th highest element, and I got an element whose rank was 10. So what is it saying? Okay, well, R is less than K, 10 is less than 46. So I'm going to throw away all the elements below that element of 10, rank 10. And now I want to find the 36th highest element. That is correct. If I throw away that element and the elements below it, or throw away the elements below it, then I've lost 10 elements. So my rank, which used to be 46th highest, 46. I got this the reverse way around. Yeah, I've done this the reverse way around. It should be. This will work, right? The way I've written it. Because it's the 46th smallest element, there are 10 elements below it. Now it's the 36th smallest element, which is exactly what step 6 would be. If my magical red element happens to have rank 52, so now it's step 5, 52 is more than 46. I threw away all the elements above that and said, okay, of these 52, I want to find the 46th smallest. In both cases, what I want to find is in fact the thing I will find. Does that make sense? That I've done the subtraction carefully now that I fixed my algorithm. Let's keep smallest, not keep largest. Would anyone like to Jeopardy style express that doubt as a question? So what I'm trying to argue is that in order to validate that this algorithm is correct, I don't care about how I found that red item. All I need to know is once I find it, I have correctly thrown away things that are guaranteed to be irrelevant for finding the answer. I have not thrown away the thing I care. And that's what steps 5 and 6 do. And that's all I need for that at each recursive step, that what I'm looking for is in fact correct. How would I prove that this is correct? By induction. I would say assume that this procedure is correct for all lists of size, up to n. If I have a list of size n plus 1, I run step 4, I get an element, and I know that in step 5 and 6, I've thrown away the correct things. I now invoke the median finding, the rank finding procedure on a set of size less than n plus 1, because I've thrown away at least one thing. By induction, that is correct, and therefore by induction, this whole thing is correct. But the key step is to observe that if I found the rank of that element, all of this is fine, that I correctly know what to do. I want to make sure that you're convinced of this, because there's really no point in me trying to show that the algorithm is efficient if we don't believe it's correct. And I'm kind of sensing that there's skepticism. So what I'm trying to get at now is where the skepticism is located in this. Yes? Yeah.
When we say median, for the kth thing, it's fine. But when we say median, we generally implement this median, we take the average of the two.
You don't have to. Like I said, I define the median as anything for which there are n over 2 below it. So you don't have, the average is one. I mean, if you think about an even list, right? Let's see here. You have a list that's even. You have all these things below. You have all things above, and you have something in the middle. Anything you choose here is the median. The average is just one median. That's what we learned in school. Okay, take the average, but it doesn't matter. Any element here is a valid answer.
Okay, so it will become
Doesn't matter. I told you I don't care. Remember, I said ignore the first 3 steps.
Okay, because if you put any.
No, but ignore the first 3 steps. All I'm saying is magically produce this red thing, find its rank by a linear scan, and then prune out things accordingly based on its rank compared to the element whose rank I'm looking at. Based on K. So step 5 and 6. All I'm asking you, or all I'm asserting, is that steps 4, 5, and 6 will give you, applied repeatedly, recursively, will give you the correct answer, regardless of steps 1, 2. Again, I don't care, but it takes a bit. I can do it. No, I don't. See, well, how long does this, we just talked about this, how long does this step take? I scan the list, I have an element, this red element, I scan the list, count how many are below. It takes linear time to find the rank of this element. No, I just scan. I go. So first item, is it bigger or smaller? Smaller, 1. Second item, bigger or smaller? Bigger. Don't increment the count. Third item, bigger or smaller? Yes. Increment the count. It's a linear scan. So this takes linear time. But again, I don't care. I don't care how long it took. I'm not asking you to think about that. I'm only asking you, is it correct? If I did in fact find the rank of this element, someone gave it to me, would steps 5 and 6 be correct? That's all I'm asking you to say. When you try to prove an algorithm works, and you have to separate out in your head correctness versus efficiency, you will often find that a lot of the work involved in making things efficient are developing correctness. And it helps to decouple these points. It helps to look at this and say, steps 1, 2, and 3 do not matter for establishing correctness. All I need to know is I have something, and it has a rank, and I can find that rank, and I can use it to split things. That's all you need to know. Because then you can say, okay, now the work is to find a good point. Of all the red points I can pick, find a good red point. So again, I'm asserting that this is correct. And I'm just giving you the reasoning why it's correct. And what I'm looking for is your questions. If it's all clear, that's good too. I'm kind of sensing there's culture over there. Okay. Out of time. But I will say this. I want you to go away and think about this. On Friday, we will finish this up. And what I'm going to then argue on Friday is that by using steps 1, 2, and 3, the rank of the element you get is such that in steps 5 or 6, you are guaranteed to throw away lots of stuff. Remember that correctness merely means that I can throw away things. But if I don't throw away enough, my algorithm does not intolerate progress fast enough to get a good running time. I have to be able to throw away a lot of stuff very quickly. And steps 1, 2, and 3 are designed to make sure that I can throw away a lot of stuff very quickly, so I get the boundary. And that's what I'm going to show you. But again, make sure that when we start on Friday, we're convinced that this is in fact correct. That assuming I gave you some element, that running steps 4, 5, 6 will give you. Okay? Alright. I will see you on wait, today is Wednesday, isn't it? Yes. I'll see you on Friday. And then we'll continue.